Okay, the other part that we are going to discuss is the division process when we deal with complex numbers, because we've talked about addition, subtraction, multiplication. Okay, in order to deal with multiplication, we need to work with something we call the complex conjugate. Okay, so the z number here, if you will, is a plus bi. Okay, its complex conjugate is going to be a minus bi. Alright, and you notice the notation here is z with a line above it. We call that z bar. Okay, or if I were to put the bar over a plus bi, okay, that notation means find the complex conjugate of that number. Okay. So if I had to take 3 plus 4i, and I call that my z, and I want to know what, or I call that my z, and I want to know what z bar would be, okay, notice all I need to do is just change the sign, 3 minus 4i. Okay. So as long as it's in that a plus bi form, if it's not, I'd put it in the a plus bi form first, okay, and then from there, it's just a matter of changing the sign to the opposite. If it's minus, it becomes plus. If it's plus, it becomes minus. So that would be your complex conjugate. Okay. All right. Now, the usefulness of that comes when we do a division. Okay. So I have a couple of examples here that we're going to use to show how to divide these complex numbers. Okay, so literally if I have 3 on top and I have 5i on the bottom, 5 minus I on the bottom that is, okay, if I want to divide these two, okay, we can't just set up a normal division and have 5 minus I out in front and then see how many times 5 minus I goes into 3 because it doesn't make any sense. True? So the way we handle this, okay, and really this would be an okay answer, except for the fact that we don't like to have radicals on the bottoms of fractions, and what is I? It's really a radical, isn't it? Okay, so that's the reason why this really can't stay like this. It needs to be simplified. So the technique is we're going to use the complex conjugate, and we're going to multiply both top and bottom by that complex conjugate. Okay, so what that's going to look like on top is a distributive property problem. We'd have 3 times 5 plus I, that would give me 15 plus 3i. Okay. And on the bottom, why we use that complex conjugate is because when we do the FOIL method, notice when we do 5 and 5, we'd get 25. When we do 5 times I, we get plus 5i. When we do the inside, we get minus 5i. And last, we get negative I squared. So again, we use that because what happens here in the middle and what's going to happen every time if we use that complex conjugate. These two are always going to what? Those two are going to cancel out. And what do we know about I squared? Is I squared a radical? Well, I squared is negative 1. True? So with that said, we'd have 15 plus 3i on top again. And then in the bottom, we'd really have 25 minus negative 1. Okay. And from there, we could change that to 15 plus 3i over 26. And that would be the simplified version of that complex number fraction. Questions on any of the algebra that I did there? Alright, so if we follow suit on the bottom one here, we do 3 plus 2i. And we multiply by the complex conjugate of the bottom. Let's see what we get on top. Notice that the top's a little bit more complicated because we have to FOIL the top because there's a binomial on the first one. But if we do that, we'll get 6 plus 4i plus 3i plus 2i squared. And then at the bottom, I'm going to have 9 minus 4i squared. And notice what did I skip this time on the bottom? I didn't bother doing the inside and the outside because what's going to happen anyway? They're going to cancel anyway. So again, that's the whole point of using the complex conjugate. Right, so let's go through and simplify. Top here, we have 6 plus 7i. And then this right here, 2 times I squared is really negative 2. So it'll be a minus 2 here because it was a plus. And then at the bottom, okay, that stuff I just put in parentheses right there is really negative 4. So on the bottom, we're going to have 9 minus negative 4, which is 13. And so my final answer, if I combine the like terms on the top, will be that. Okay. You might want to take a guess at why most people get this problem wrong, or any problem like this? What do people generally mix up, you think? All these pluses and minuses and I-squareds and whatnot. Most people get the signs wrong when they do this. That's usually the most common mistake. So when you're doing this, just make sure I always try to show every step. That way I know I got my signs correct from one step to another. So if you just try to do this all in your head, you might be able to do it. Okay? But I would suggest that you do it like I show you. That way you're going to have a pretty good chance of getting it right every time. Okay, so one of the things that we're going to work on in the second part today is that. Okay, and then I started today talking about the discriminant, and here's the answer to what I started discussing with you yesterday. One of the purposes for dealing with imaginary numbers is that sometimes quadratic equations have imaginary solutions. Okay? So, for instance, in this particular case, when we have a quadratic equation, the first case is if b squared minus 4a equals 0, and remember this is the discriminant. Okay? So this expression is the discriminant. If it's greater than 0, then we have two distinct real solutions. Okay? Which means, relating this to what we know about graphs, is the graph would have to look something like that. There's two real solutions. Okay? And when we did that yesterday, when we solved with the quadratic equation, we always got two real solutions. Okay, if the discriminant equals 0, then there is one repeated solution, which graphically is going to look like this. Okay, we have exactly one spot where the curve touches the x-axis. Okay. Okay, so this particular case is going to be this. And then finally, there is a situation where the discriminant could be less than 0. If we calculate the discriminant and it's less than 0, okay, then there is a pair of complex solutions. So that would be this case here, where we have a parabola that doesn't cross the x-axis. We don't see any real solutions. We'd never be able to find with a calculator because there's nothing to find when we do the 0 command. Okay? However, does that mean we can't still solve that quadratic equation? No. Now that we know about imaginary solutions, we can still follow that same process. Just when we get done, our equation or our sentences are going to have i's in them. Okay. Okay, there's one other fact about discriminant that I want to put down here that you can use to your advantage when you're doing any kind of quadratic equation, and that's this: if the discriminant is a perfect square, then the quadratic is factorable. Okay. So any quadratic equation that you've ever factored in the past, if you would have checked its discriminant, you would find that then the answer is a perfect square. Okay? And that's something that you can factor. Okay. Questions so far? All right. So let's go ahead and put that into practice by solving this quadratic equation. Okay, I'm going to use my technique that I showed you yesterday, my set of steps, which is step 1, find the discriminant. Calculate the discriminant. Do your b squared minus 4ac. So in our case, we're going to have 4 squared minus 4 times 3 times 5. And when we do the discriminant this time, we're going to get 16 minus. And in the parentheses, we're going to have 4 times 3 times 5. That would be 60. And so therefore, my discriminant would be negative 44. Okay. So we already know, because it's a negative discriminant, that we're going to have two imaginary solutions here. And if we were to graph this, we know that we would see no y-intercepts, or x-intercepts, I should say. Okay, so we know those two facts. Step 2 was to take the square root of the discriminant and simplify that. Okay, we know for sure that that can be negative 1 and 44. With 44, we know that 4 goes into it also, so we can simplify that as well. And so when we get done, like we did in the first problem today, that becomes a 2, that becomes an I. So we'd simplify that to 2i radical 11. Okay. And then finally in step 3, we'll plug everything in. So we'll go -4 plus and minus 2i radical 11 all over 2 times a, which is 6. So step 3, we'll fill in the blanks on the formula. Again, the big blank that we already know, we can just plug that in there without having to do it all over again. And one more step to get a final answer here, because we noticed that the 4 and the 2 have a 2 in common, and so does the 6. So if we factor out a 2, okay, we can reduce all those by 2, and we just get I radical 11 all over 3. And that would be our final answer. Now, unlike some of the ones that we've done so far, okay, this is going to be a lot more difficult to check. Okay, because can you type this into your calculator, into your table function? Nope. Okay. So if you really wanted to check it, which depending on how much time you have, okay, could you take this thing and square it, multiply it by itself? Okay, we know how to multiply complex numbers together. We learned that earlier, right? So we could square it and then multiply it by 3, and then also multiply it by 4, add those two together, and then add 5, and hopefully we get what? We get 0. It'd be pretty tedious to do the check here, but it's doable. You can do it. So if you have enough time, if you're done with the test and get 20 minutes left, why not do it? Rather than turn it in early. And if you got time, do it. Okay. The assignment then for tomorrow is to work on your P6 work.